So it is really my pleasure to introduce Fumin Wang. He is probably the student in my first class, if I remember. I'm not sure, roughly. That's
Thanks.
about the old, more than 10 years ago, or maybe 15 years ago, when he was undergraduate student in our department. And certainly he is one of the best students at that time. And so I'm very happy that this is another time for him to contribute what he learned recently to our department. And actually, um, his experience is very interesting because after, maybe he will say that later, but after his graduation, he went to the, I think the business school, right? To do
Yeah,
the
yeah,
economics
yes.
or financial, to do financial thing, something like that, and to get his master degree. And then he had a chance to work on an IT company, especially in DeepMind, which is now belong to Google to develop AlphaGo. Before, I think he was also part of the member in the team. And now he went back to Taiwan and want to develop his own career. And maybe he's working on blockchain or something else. So I think I'm not very sure about this, but he could also introduce himself more during the lectures. And you are also welcome to ask him more questions about how to apply physics or machine learning techniques in a real industry or in a future career. Okay, let's welcome not professor. Wow, let's welcome Fumin. Okay, yeah.
Thank you. Yeah, so yeah, I was a student of Dawei, I think, yeah, like 10 or 15 years ago. And then I sort of like really liked computers. And so I eventually did work in the software industry, and then most recently in DeepMind. And so, but over the course of these years, I've always thought that the physics principles that I learned during my college times was immensely helpful. And so I thought maybe this would be a good topic to share with everyone today. So yeah, during this talk, I want to share a couple of applications of the things that I learned in physics that are surprisingly useful to the kinds of AI applications that I've did before. So let me present this. So yeah, so the first physics application that I want to talk about is the heat conduction. So right here is an app on iOS. I don't know if you guys, some of you guys are using iPhone. You can find this app. Yeah, it's displayed here, and this app allows you to say take a picture in this middle, for example, a guy swimming with a dog, and then pick another picture of a dog that is pretty different from the first image. Just roughly select the location of the dog, and then you can combine this dog like seamlessly into this second image. So this is what this app does, and now I want to do a live demo to show you that this is real. Sorry. Yeah. So I guess all of you can see this screen. So this is a simulator on my computer, and then this is just some funny image that I have, and then now I say I pick an image of this other guy, Obviously, they look quite different. And then I select it, and then you see, like, if you just do the ordinary thing, there is some weird boundary here that you can see. So this is the normal thing that we would do. But now if we try to apply some physics principles, and then we'll see that we get a much better effect. So let me just try to show you how it works. Okay, so okay, and now so we are going to try to apply the heat conduction principles on this image. So we'll do the same thing. We'll select this picture. We'll select the area that we want. And just a rough contour. And then we see that by applying the physics principles of heat conduction, we can see that it sort of blends into the background. So this is roughly what I want to explain how this works. For example, if we flip it, then it becomes much better. Yeah, you guys can play with this later on if you are interested. So let me go back to the slides. So how is this even possible? Like trying to blend this into the background. So the most important intuition here is to treat this image as let's say RGB values, and then let's say we imagine these RGB values as temperature on some object, some material, and so we can say that the darker the blue here, the higher the temperature. Then the lighter the blue here, the lower the temperature. And then what we want to ask is that, so obviously here, there is a sharp drop in the temperature. And so this means that this should not happen in equilibrium. We know from physics that if a system is in equilibrium, then the difference should be very smooth. It should not have these abrupt changes in its physical properties. So this is the main intuition here. Is to imagine images as temperatures. And so specifically, what we would do is let's say this we denote this contour as omega. So omega is this red box, and then we say that out of the outside of the contour, we denote it as f star. So f star is a given, and then we denote the temperature inside the region as G. So it's like we have two metal plates. Then the temperature on the outer metal plates is F star, and then the temperature in the inner metal plates is G. And then we ask, what if we put G inside F star, and then let's say wait for a few hours and lets them reach the equilibrium states, what would be the new temperature F inside the region? So let's imagine that the temperature inside the area would change by T, and so the new temperature would be the original temperature plus T. And then obviously we want the boundary here to be smooth. And so we know that on the boundary omega, T equals F star minus G. So this is the boundary equation, the boundary condition that we need to satisfy. So here we know, we already explained that the intuition that we have here is the heat conduction phenomena. And so we know from physics that the heat follows the heat equation here. So the change in temperature is proportional to the gradients of the temperature. So we know that the exchange of RGB values or temperature must satisfy this equation. And then we also know that during equilibrium, the temperature or the RGB values should not change. So zero, so we can simplify this equation to 0 equals Laplace T. And so all we need to do now to seamlessly blend, say, the dog into the swimming pool or the face of another guy into another guy is to simply solve the Laplace equation. And so you might say, okay, so problem solved. We simply need to solve this equation and then we are done. But then if we really want to get our hands dirty and to say, like, create something real, we need to come up with a way to solve this Laplace equation, which is not that straightforward to solve. But fortunately, to solve this equation, we can apply physics again to solve this equation. So imagine that the area that we want to solve, the image. So these the image here, these dots are pixels, and then we can, sorry, it seems that there is the lag. Okay, cool. And then so this is, say, this is ij is the pixel that we are interested in, and then pixel ij plus 1 is the pixel to the right, I minus 1 is the pixel upwards. And then to solve the equation, what we know that is, in order for this system to reach equilibrium, these pixels or these vertices should exchange their heat. And so this gives us makes a guess. And so our guess is that, let's say we want to calculate the temperature at time step t plus 1. And with what we simply do is we'll just average the temperature of the nearby areas, and then up and divided by 4. So this is the average value of the new pixel. And so this equation here simply means that the heat is being transferred from the nearby regions from high temperature to low temperature. And then here, so if we do this heat exchange for a large number of times, then eventually we'll reach equilibrium where there is totally no heat transfer. And then in this case, the state of this system, or the RGB values of this image, would be the result of this image cloning. And so this is kind of a neat example of how physics principles, in particular heat conduction and the Poisson heat equation, can be applied to image processing in AI. And so this is the first example. And then the second example I want to share with you is to turn a photo into somewhat like a pencil sketch effect. So here the left-hand side is an ordinary photo, and then the right-hand side is an automatic way of turning it into a pixel sketch. If you're interested in like more examples, you can click on the link here. And so what I want to do is to describe like how can we teach a computer to automatically do pencil sketching. And so I guess you already know that what we're going to do here is to apply physics principles. And the first thing that we notice in a pencil sketch is that very often, more often than not, we'll see these protruding, let's say, artifacts of pencil sketching. So here is a close-up of this signboard, and you can see here the artist has some like shady protruding sketches, and what we want to do is to mimic this kind of artifacts. So the way that we're going to mimic these kind of artifacts, simulate this kind of artifacts, is to apply a convolution. So I guess most of you are pretty familiar with the concept of convolution in continuous space. But I just want to sort of just to recall what convolution does in the discrete case. Let's say these are the image, the pixel values of an image. And when we say we're doing to convolute this image with this patch, so we can imagine this patch as measuring the gradients on the x-axis. Because it is this value minus this value, and then we get 3. And so we know that on this pixel, the shape is sort of on the x. There is a slope on the x-axis. And so if we convolute across this image, we sort of like measure the difference in the x direction and the y direction. And so here is a real example of how of the effects of convolution on an image. So here we have an image that has grids and numbers in it. And so if we apply the convolution on this filter, on this kernel, we see that it detects all vertical patterns in it. And then if we apply this, and then we'll see that it captures the horizontal effects on this. So this is sort of like applying Fourier transform, where this is one of the bases, and this is another basis, and then we sort of like capture the salient features of this original image or this original signal. And so essentially how we mimic this sketchy artifact is we apply kernels on every direction, and then so if there is a sharp gradient here, the convolution effect would capture this and then give us this nice effect of a pencil sketch. So this is the first thing that we do to mimic real people pencil sketches. But in addition to that, to make it more realistic, we need to make sure that the interiors of the image look like real pencil sketches. More specifically, we want to make sure that the coloring of this image looks like the image on the top right here, which is like a real person pencil sketch. So the way we do this is to let's say we denote the original image as J, and then H is our patch, and then we'll draw multiple times of H to mimic the pencil's sketch. So here if we draw it 0.2 times, we get pretty fair image. But if we frequently draw it, then we get a darker image. So in mathematical terms, we want to find beta. So beta is the times we draw the image patch. We want to find beta at each pixel so that h to the power of beta is equals to j. And then in physics, especially in statistical mechanics, the one trick that we often do is to apply the logarithm so that we can deal with only with addition and multiplication instead of exponent power. And then so this gives us this. We want to find beta such that beta times this equals this is as close as this. And then so in addition, we want to avoid cases where there is an abrupt change in beta, because this is not what artists do. So we also require that beta is locally smooth. So essentially we want we say that the magnitude of the gradients of beta should be as small as possible. And so the full objective here is simply such that h to the power of beta equals j, and then we want beta to be smooth. So this is, so we know h, we know j, and then we simply solve for beta. And so if we recall what we did previously with image seamless cloning, what we are saying is that in image cloning, we say we want to make sure that the gradients of our adjustment to be as small as possible. We want the minimum adjustment so that f and g are close. And then this leads us to the Laplace equation. So if we observe these two equations look pretty alike, and so with some similar mathematical tricks, we can say that this leads us to the Helmholtz equation. So that's pretty neat. The Helmholtz equation is something we are familiar with. It's similar to the wave equation, and so this brings us back to physics again. But I think perhaps the more profound analogy we are seeing here is that very often in artificial intelligence or in machine learning, we say that we want to minimize some we want to satisfy some constraint, which is often expressed as a loss function. So we want to find the minimum of something, and then this leads us to a partial differential equation. And so in physics, what we actually do often do a similar thing in physics, in which we say we want to find the minimum of the integration of our Lagrangian, and then this leads us to also a differential equation. So in this case, it's the classical mechanics equation. And so we see that in physics we have this least-action principle. So although it is less used in daily lives, it's actually a pretty useful, inspiring way of describing the world in terms of like minimizing something. And in fact, in artificial intelligence and in machine learning, this kind of description is actually the more common way of describing the phenomena that we want to describe in AI. So this is essentially the second thing that I want to share with you guys. And so in conclusion, I think the main message that I want to convey is that over these years, what I found really useful is that physics intuitions and they actually surprisingly occur in many different places like that I couldn't imagine. And then also in mathematics, we often encounter hard problems, but then if we are able to find the appropriate analogy to physics, then thinking in terms of how nature works actually can provide us with cool solutions to these hard computational problems, such as the Laplace equation solver that we just saw. And then last but not least, I think physics also plays a very, very important role in our way towards AGI, or artificial general intelligence. And so I guess most of you by now already know that when people say they want to solve AGI, they often entails the development of reinforcement learning. And in reinforcement learning, we essentially say what we want to do is we want to create an environment that is as rich as our real world. And so this is obviously this is an extremely tall order. We haven't really known all the physical laws of our universe. And so so that means it's going to be very hard to create a virtual environment that is as rich as our universe. And then also, in addition to this, we also want to create an agent that is, let's say, as smart as human beings, that has a computational capacity as impressive as a human brain. And so here, so in this formulation, how does physics help? So physics, first of all, physics helps with describing the fundamental laws that this environment should satisfy. So for example, there is this pretty interesting paradox called the pain-leaf paradox. So this is very interesting. So so previously in the physics department, I've always this impression that classical mechanics is a solved problem. There is nothing new or interesting in classical mechanics. But if you look up pain-leaf paradox, you will discover that this is not the case. So there is a lot of work we physicists need to contribute. And then secondly, of course, we know that our computers today, let it be GPUs, TPUs, or supercomputers, they're not even as, they're less powerful than even the brain of a mouse. And then there are speculations that our own brain might require quantum effects to work. And then so this all implies that like physicists who work on quantum mechanics should contribute to AGI too. And then so yeah, so this is all I want to share for today. And thank you, everyone. Yeah.
Thank you for this wonderful talk.
Yeah, you're welcome.
Okay, we have quite a couple of time for people to ask questions. And this is a Q&A time. And feel free to unmute to ask your questions.
Can I ask a question first? Yeah. Hello?
Yeah, go ahead. We can hear you.
Okay. Yes. For me, that's very interesting for using physical law or these equations to solve certain complicated problems, as you mentioned. But actually, this is probably just a kind of analog, I think. So it does not mean that it is real physical problem to do this correctly, right? So
Yeah.
For example, like a Poisson equation you mentioned, that or Laplace equation you mentioned inspired from the heat conductance. But actually, in principle, we could always derive another equation, right? And maybe non-Laplacian, but maybe Laplacian square or something that which could maybe do a better job. But it has nothing to do with real physics law we know already. right? So
True, yeah.
right. So there's no, because for example, when you merge the two images, in principle there should be no true answer, which result is more physically correct, because there's no such things appear, right? So
Yes, exactly.
yes, right. So it's kind of inspired by physics. You can say this way, but or you can, or maybe we can say that for AI engineer or scientist who are trained in physics background may have some better idea or some concepts inspired from physics law to solve the problem we have to do in computer image or in machine learning. But it does not mean that the only way to do this is from the physics background. Yeah.
Yeah. True. Very true. Yeah.
Okay,
Yeah.
okay,
Thanks
just
for
one.
pointing this out.
Yeah, that's okay.
Yeah. So I think this is I think so I've throughout the talk I've emphasized the similarities of physics and AI, but I think it's also like interesting to point out the differences between physics and AI. So I think like Dawei explained in physics, like the Poisson equation, the heat conduction law is a law, at least in the macroscopic sense. So it's universally true. It's definitely true. But then in many applications in machine learning, there is really no one true answer. A lot of times, a lot of applications actually is related to aesthetics. So it's kind of subjective whether or not the quality of this image generation model is better to the other one. So there are indeed a lot of differences here. But I think it's but I think it's kind of like surprising that like a lot of these mathematical formulations can carry over to the artificial intelligence space, and then the results are kind of like acceptable, cool. Yeah.
Fumi, can you say more about the concept of this AGI? What's the difference between AGI and the typical term of AI?
Yeah. Good question. So I think the term AGI with the G is a relatively new term. I think people started become interested in AI since the 1960s. But then I think it's only until like the 1990s where people sort of start to ponder what if we have an AI that is like really in general. And so I think there isn't really a widely accepted definition, like mathematical definition of what AGI is. I think for most people, AGI simply means HAI, human intelligence. I mean, an AI that is as good as human. So I think this is the most commonly found definition of AGI. And then I think I also want to mention something interesting is there is this, for those of you that are really curious about what this is, there is actually a subfield of AI that's called theoretical AI. So similar to theoretical physics, it's a relatively small field like theoretical physics, and then it's also like extremely mathematics heavy. And so in theoretical AI, what they're interested in is questions like what does it mean to measure AI that is smarter than humans? Or they might be also interested in questions like, let's say we have an AI that is very powerful, And how can we make sure that the AI is within our control? Or more specifically, can we design a rate button? So I guess some of you might know that in like say a car factory, like real robots often have a rate button. So if a worker sees something like wrong, it can smash the rate button immediately, and then the entire robot will stop. So taking this analogy, those guys in theoretical AI, they would also ponder on this question of whether they can mathematically prove that we can have a rate button that the AI itself cannot circumvent. So yeah, it's kind of like an interesting field, AGI. And then I guess some prominent researchers in this field include Marcus Harter. Yeah, I recommend like his books. Marcus Harter, Marcus, and then Harter, Hutter. Yeah, so that's roughly what I know about AGI.
Thank you.
Yep. No problem.
Fuming, thanks a lot for this nice presentation. So I'm wondering if physics can help us to work backwards. For example, you show how to produce an image that looks more realistic than traditional image editing tools. And we know that deepfake is now, in some sense, a serious problem in transmission of information. There are many fake news around. And do you think physics can help us to identify what is deepfake or not?
Yeah, I think physics most probably can help. And so in terms of specifically how physics can help, I think maybe so obviously I'm really just guessing now, like really no one right now knows how to tackle this very, very important perhaps like social problem of having fake videos and fake images all around. So I think I think perhaps the underlying problem here, as in a lot of cases, is we don't really have a good efficient automated way of measuring how fake an image is. So I think there is this old adage that goes as if we can measure something, then if we can quantify something, if we can put it in mathematical terms, then the problem is perhaps already solved half. And so yeah, I think so I think like actually if we look at the history of AI, we often see that the major breakthroughs in AI is often when people thought of some like quantified way of measuring progress, like say in terms of speech processing and image recognition. So in image recognition, it would be the accuracy, and then let's say in natural language processing, it would be the Rogue score. But then, for example, the Rogue score in say text summarization is perhaps not a very good way of determining whether summarization is good or not. And I think that the hard problem, like in many hard problems, for example, in fake images or say adversarial examples. For example, like text summarization, is that it's or like image cloning. It's hard to say whether this summarization, this abstract is better than the other. And so I think what physicists can help is, I think like historically for the past several hundred years, like we physicists are very good at creating like apparatus, like experiment apparatus that are very, very precise, that can measure things that, for example, like whether or not the inertial mass or the like weight, I forgot, sorry, I forgot, or the weight mass, like how are these masses equal? But then there are physicists that are so creative that are able to measure this kind of slight differences. And so I think the first thing physicists can help is to devise smarter ways to measure progress. And then I think similarly, I think physicists can help is to turn these like murky, vague, like ideas, intuition into like concrete mathematics. So I think these are really like really traditionally strengths of physicists, like turning like murky ideas into crisp mathematics. So yeah, these are just my guesses.
Thanks. Thank you very much.
Yeah, no problem.
Are there other questions? Then I can ask the next question for no further questions. And could you comment on a bit your personal experiences when you got a physics major and then transition to computer science career? So what's the challenge you experience, and also what's the advantage you see that being a physics student and working in the computer science?
Yeah. So I think as a physics graduate, one of the main I think one of the main appreciation that I have for AI or computer science is that suddenly, like on a computer, it makes like applying theory into practice much more straightforward. But so obviously I understand that like modern physics, it's no longer affordable for a hobbyist. So in order to like really make like state-of-the-art physics experiments, I probably need several $1 million to set up a lab. I need to like a high quality vacuum. I need to have high quality lasers in order to do something interesting in physics. But then in comparison, at least at the current state of AI and computer science, it's like I can just have a laptop and I can do like really see the effects of these theories right in front of my eyes. So I think coming from a physics background, this was I think one of the appeals to me why I was interested in AI. And but then as I dive deeper and deeper into AI and computer science, I actually slowly have this opposite feeling that wow, like the the education that I received is like really, really immensely helpful. And this is there is like really, really concrete example. So for example, I guess by now most of you know that in AI, the neural networks are in the vogue, and then within the field of neural networks, backpropagation is sort of like perhaps the one most important thing in AI. And then backpropagation is really like coming from a physics background. Like this is like simply like straightforward thing. Wow, it's just partial derivation. But then like I often observe like people coming from less physical background, like coming from a computer science background, like I observe like hard conceptual gaps. Like I think traditionally computer science students are more comfortable with like discrete mathematics, and then when they see, wow, like infinitesimal things, wow, integration, differentiation, wow, and then it's like really like alien to them. But I think like fortunately coming from a physics background, like these things are like really, really familiar. And then I think like even if we go deeper into AI, like people like most often the language here is often statistics and probabilities. And then so now we not only have like integration, like calculus, we're dealing with divergence, correlation, like these kind of concepts. And then coming from a physics background, like these like really makes it much more natural. So yeah, these are like my main experiences.
Yeah, thank you for this very concrete experience sharing. And in your current working environment, and is a diversity important? For example, in your collaborator, are they still mostly computer science major, or you start in the growing of people from multiplicity background, and they have to learn how to talk and work together?
Right. Yeah. Indeed. So I think from my experience in DeepMind, so within the research group, I think perhaps there is actually in terms of like proportion, there is I think less than half of the researchers in DeepMind have background in computer science. I think of course like most of us did a PhD. Most of them did a PhD in highly related fields in AI. But then oftentimes, like from what I know, like a lot of them they did their undergrad grad in physics, in math. So I think aside from computer science, there are a lot of people whose backgrounds are in physics and maths. And I think if we look at the prominent researchers in the field, like Jan LeCun, like we'll see that their background are indeed in physics and maths. And then I think also in DeepMind, there are also a lot of people who come from chemistry. And then I think I know that a couple of guys who actually did their PhD in sort of like computational chemistry. So it's totally totally not in the field of AI, but I think they all bring, like you said, diversity, different ways of thinking, different skills, different mathematical skills, computer skills, and then different ways of seeing things, of describing nature. So I think obviously DeepMind wants to tap into the diversity here from these researchers.
And do you think DeepMind is special here, always a general trend. I visited Taiwan AI Lab 2 months ago, and I realized that 100% of the employee coming from the computer science major in Taiwan. And they also start talking about they should start increase the diversity. But even though they talk about this for a few months, they did not successfully hire any people whose major are outside the computer science. So do you see there should be a global trend also in Taiwan, or is any specific effort that the AI development in Taiwan should improve?
Right. Yeah. So yeah, I think it's a pity that yeah, the AI lab hasn't caught on this trend, and I think you are right that globally speaking, this is definitely a trend that I think is going to prevail, like in the going forward. I think in terms of what the community here in Taiwan can do, I think is I think first of all is to appreciate that the values diversity can bring. So I think in DeepMind, I think there is a conscious efforts to bring in inclusiveness. So I think there are efforts within DeepMind, say to celebrate. So there is a celebration for Black People Day. I think it's a commemoration of some events in Africa, for example. So this is to bring Black researchers into the DeepMind family, and then I think DeepMind is also a sponsor for an Eastern European AI conference. So obviously, located in Eastern Europe implies that this conference has limited resources, like say to invite speakers or to provide like accommodation. And so DeepMind is realized this and is a sponsor for this. And then I think the sponsorship for that East European conference was initiated by a colleague in DeepMind who comes from Eastern Europe. So I think from Bulgaria, and so I think these are examples of perhaps what the community in Taiwan can do. Yeah, I think definitely, and then I think in a more long-term point of view, I think like broadening the scope of our education might also help. So I think personally, I benefited a lot from the kind of like really wide perspective as a physics student, like realizing that wow, physics can be applied to fields as far as economics. I think there was a course by Lin Xiuhao Lin. Yeah, that was had a really big impression on me. And then, for example, like realizing that wow, like quantum mechanics, and then spin, and then these are like really fascinating topics. And then they have wide, in addition to just lab experiments, they have wide applications to our real world. So these are really like inspiring experiences that I have. So I think maybe if we can put more efforts on this kind of things, there would be more like cross-disciplinary opportunities.
Yeah, this is great. Yeah. Good.
Yeah.
Any Any other comments or questions from the class?
Okay.
Okay, and Jennifer, I think it's now 15 minutes. Do you think it's time that we can call for the meeting?
Yeah, sure. I think, and thanks a lot, Fuming, for this very nice presentation and your feedback and insights. So I think we can close the meeting.